I'm David Waterman, and so this presentation is going to be about writing tests for data science. My intended audience here is people who probably have not written any tests, or they have written some tests, but maybe not necessarily for data science work. And so I'll do a little bit of background about why you should test your code to start. I'll talk about the reason that I came to this problem in the first place, why I decided that we needed to start testing. And then at the end, the last section will be about actual practical implementation. I'll pull up some code and we'll write some tests and look at them together. So before I get into the actual practice of writing tests, I want to take a step back and think about why you should bother writing tests and how to think about them. So I actually, before I was a data scientist, I was a high school math teacher for 9 years. And so that's kind of my go-to when I'm looking for analogies. So if you think about your high school education, it was probably very similar to mine. My math teachers generally would give us homework problems out of the textbook. They would send you home with a page number and a list of problems to do. And a lot of the times, the answers to the problems would be in the back of the book, right? And so my big question that I actually like somebody to respond to, so just yell out for me, please, is what's the point of giving students homework problems if you're going to give them the answers that go with them too?
Refine the process of getting the answer.
Refine the process of getting the answer, right? And anybody else want to, I heard someone over here say something. Check yourself afterwards, yep. And so, is your teacher really trying to get you to get the right answer if they're giving you the answer to start with? Is that the goal? And what does it mean to learn? Why would you bother going through all of these problems to learn? So you can figure out how to solve equations, right? So you can actually figure out the process to get from the problem to the answer, right? The answers are here to make sure that you did the path correctly, but the goal is to have you practice getting from the start to the finish, right? And so if you know where you're going, you can always tell if you're moving in the right direction. If you begin with the end in mind, you can make sure that as you go through the steps, you are moving towards your goal, right? Well, many of our daily tasks are like homework problems, right? You have some kind of problem that you're trying to solve, and you know in your head how it's going to look when it's done. You know the output that you're expecting. You know the results that you want to see. And you just need to figure out how to write the code that's going to get you to those correct answers. Well, if you start writing your code with that mindset, that's really similar to the test-driven development. And so maybe we don't all necessarily use this process intentionally, but the idea is that if you're going to do test-driven development, which is common in software engineering, you start by writing a test for the code that you're going to write before you code anything. And then you work on writing that code and running the tests until you have a passing test. Then you take a step back and see if there's anything you can do to refine what you've written. See if there's any refactoring improvements that you can make. And then you move on to the next task. And if you break your problem down into small, bite-sized chunks, you can just go through the cycle over and over and over again until you have what you need. So when we talk about testing our code, there's lots of reasons why we can test our code. For other people, the people who are going to be seeing your code or your work, the output that you produce, having tested code is nice because it's going to reduce your bugs. It's going to improve feedback loops, so it's going to make it easier for you to see things that you'd like to improve. It's going to speed up iteration, make your code more reusable, and it's going to increase other people's confidence in the system that you've built. For you, it's going to make other people trust you and your work more because they're going to see that you've already tested it out beforehand. It's going to earn you respect from the people that you work with. If you work on a team with developers, engineers, they have to do this already. It's not optional for them, right? And so if you're doing the same work and making the same contributions, that will get you more respect. It allows you to submit to open source projects. Most open source projects, they won't let you add code without having it tested as well. And it's probably going to be required to get your code accepted into an external code base. You know, if you are contributing code at work, you know, there are lots of different ways that data science is implemented in different organizations, but it seems like the direction that people are moving now is that we are moving from siloed data science work, where people work independently on their own, into integrated data science work, where data scientists and software engineers and project managers and testers and everyone is all working in one group together, right? And so if your organization is moving in that direction, your code is going to start being looked at by more people. They're probably going to want you to start contributing to the same code base as everyone else, and tests are probably going to be a requirement for you in the future. Okay, so that's why we should test our code. The reason that I got to this problem in the first place is because where I work, we were trying to do supply chain insight. So basically, our customer buys big, complicated things, and they know that when they buy it from a vendor, that vendor didn't make every single part, right? There's a supply chain behind it. So I'm going to use cars as my example. So when you buy a car, you know, from Toyota, Toyota didn't make the tires, they probably didn't make the brake pads, they didn't make the starter motor, right? All of those were sourced from other places. And it's not just a list of suppliers, it's a tree, right? So the brake pads might have come from one direct vendor, but the transmission has bearings in it. Those were probably purchased by the transmission maker from somebody else. You know, the bearings have metal in them. Those bearing makers probably buy their metal from somebody else. And so to figure out all the different companies that are in that supply chain and all of the different places where you have weaknesses is really complicated. None of those companies want to share that information, surprisingly. So what we were working on is we were using news articles. We were just taking unstructured text and processing it using natural language processing and trying to identify the relationships from those news articles. So if it says that Takata is making airbags for Toyota, that's what we're trying to figure out. Now, the difficulty with that is that the structure of text is domain specific, which means that regular people don't talk the same way that, you know, automotive news journalists would talk about this issue. So you can't use a general text model to analyze this information and really get the same results that we want out. You know, if you read the first example up here, it says, per the long-term agreement, WABCO will supply its single piston air disc brake technology, MAX, for the manufacturing of Hyundai's new medium-duty trucks, which are expected to start from August 2019. Well, that's not really the way that most people talk. It's not the way most people write. And so if you use a general model, you know, if you just go on GitHub and find something to try to, you know, pull out the useful information from that sentence, it's probably going to fail. So we have been trying to create our own model that deals with this type of text structure better. But the problem is that, you know, when we started out, the model was really bad. We were getting maybe 10 or 15% of the sentences that we were processing were giving us the output we were hoping for. And so we decided we needed some way to measure and benchmark it so that as we worked on the model, we could see if it was improving or not. So our approach that we used is we're calling them gold tests. And humans can read the text, figure out the relationship from it, and then put it into a machine-friendly format like JSON or YAML. And then we can write a test that's going to run our data processing pipeline and compare it to the manual test data and see if there's a matchup or not. So a human would write this example code on the right, and then we would load that up and run a test and compare the test output to this output. Okay, so now let's actually look at some code. Before I pull up my repo, I'm going to be using Pytest as my testing framework. So there's a lot of them that are out there. Pytest is one of the most popular ones. I like Pytest versus using the built-in unit test or doc tests or nose or whatever. For these reasons, it's more Pythonic. It's easy to write. There's less boilerplate. You can still run all of those different types of tests. So if you've already written unit tests, Pytest will still run them correctly. And then it's got a lot of nice add-on features, like you can generate HTML reports, and it's got a really great documentation set. And there's guides and example code in the documentation that's really handy. The only downside is it's not a built-in, so you'll have to add it separately to your requirements. Okay, so for data scientists particularly, we're not just testing our code, right? We're going to test code the same way that the engineers test code, and we're going to make sure that we get the expected output. We're going to test and make sure that it can handle bad input, and we're going to test for all the edge cases we can think of, and as they come up, we're going to keep adding edge cases to our tests. But generally, the software developers don't have to do tests on data and models, and those things are critical for the work that we do, so we need to make sure that we're testing those things as well. So we want to test that the data that we're using is valid, so we can write tests just to look at our data set and make sure it is what we think it is. We want to make sure that the types are correct. You know, if you just do like pandas read CSV, you want to make sure that the types that you're getting in each of the columns are what they're supposed to be. And we want to make sure that we're handling missing values correctly. And then for models, when we're talking about testing your model, so after you've created a model, you want to test that the format of the model is correct. You want to test that it's producing the expected results. The reason that we were doing that is so that we could benchmark it. We were saving our results every time and comparing them over time, seeing how our performance was improving. And you can also monitor for model drift. So you can't just use one model forever. You're always going to be trying to improve it, right? But if you do leave your model unchanged, but the data changes, suddenly the matchup between your model and your data is going to start to drift apart. And so if you've already saved these benchmarks, you can go back and compare and see how that's happening. Okay, I'm going to pull up my repo. If anybody wants to follow along, you can just go ahead and clone this. My plan is that I will pull it up and talk about a few things and then try to do some live coding for some tests. So we'll see how that goes. But I already have the finished tests saved in the repo, so in case I mess anything up, it'll all be there. And I'll just pause for a second in case anybody's going to download that. It's pretty small. If you're like me, you're probably going to make a new virtual environment. There's nothing crazy in the requirements. It's just standard, you know, pandas, NumPy, sklearn. Okay. Cool, so let me just clone my repo. I'll make a new virtual environment. And so then I'll just install my requirements.txt. And then the easiest way to get this working is if you have a setup.py file like I have, and you can install this repo in editable mode. So to do that, you say pip install -e for editable dot. And so that's going to install the PyData DC testing as a package that I can then import. Okay, so the code that I'm going to be testing is just like a simple example script. There's a couple kind of toy methods in here, and we're going to just kind of go through them and write a couple tests so you can see how simple Pytest is to use. So My first method is one that just gets the time and then gets a string to go with that time and returns that, so nothing special. Since it doesn't have anything as input, all I'm really testing is making sure that my output is valid. So let me go to my tests, and we'll move the existing test file. Okay, so I'm starting a new file. If you have a subfolder in your project called tests, and you name all of the files in that folder with the test prefix, Pytest will find them automatically, so you don't have to do anything special. I'm going to be using some Pytest features, so I'm going to import Pytest. I'm going to probably want to use some date time stuff, so let me import that. Okay, we'll start there. So just to write your first test, all you have to do is create a new method that has test as the prefix to its name. So we'll just call this one test get time str to match the name of the method we're testing. And so with Pytest, we normally want to use assertions. And so we're just going to make an assert statement about some kind of equality. So my output, I want to see a year, month, date, hour, minute string. So I'm just going to write a test that says that. So maybe I'll say something like, oh, and let me also import my package here. So we're going to say from PyData DC testing, import experiment. That's the name of this file up here. So maybe I can say something like, I'm going to call this experiment.getTimeString method, and I want to assert that its output is what I think it should be. So I think it's going to be a string generated by datetime, so let me just generate a string from datetime. Okay, so I'm going to get the time right now. And I'm going to give it a format that I want it to make my string in. So I want my format to be year, month, day, hour, minute. And so that's my first test. Is this output that I get from my method going to give me the same result as this datetime method does? So I just save that file. If you named everything correctly with the test prefixes, you don't have to say anything except for Pytest. And it runs. When you look at the output, by default, each test that you have created is going to be represented by a period if it passes. So down here, I've got a little dot next to the file name. So I've got one test, my one test passed, and so one passed in 0.63 seconds. All right, cool. So I can keep writing some more tests. So the next method I have is called increment. All it does is it takes the input, makes sure that it's a number, adds one to it. So let's write a test for that. All right, so it's easy to think about the default case. The default case is I give it an int, I get back an int that's one bigger, so let me write a test for that. If I give it 5, I want to make sure that I get 6 back. But I'm not just writing tests for my simple cases. I'm writing my test for every edge case that I can think of. So maybe I also want to test, like, if I give it a negative number, I should probably get something, like if I give it a -5, I probably want to get a -4 as my result. Maybe I should probably test for like a decimal. So maybe I can say if I give it 0.5, I would like to see 1.5 as my output. But if you look at my code, I also have some error handling in there. So if you pass in something that's not a number, it should raise a type error. So why don't I test something like that too? With Pytest, you can test these exceptions pretty easily. You just use with pytest.raises, and then you tell it what type of error you're expecting. So I'm expecting a type error. And then you call whatever's going to raise that error. So we're going to say experiment.increment, and we'll give it a string. And maybe I also want to think about like, okay, what other things could people do to try to throw this off? So maybe you could pass it a none. So let's make sure that it does a type error if it gets passed a none also. Cool, so these are like all of the different inputs that I'm expecting that I can think of off the top of my head. As I come up with more, I'll add them to this test case, but for now we'll just go with this. So I'll just save this and we'll run Pytest again. And if I typed in everything correctly, I should get 2 dots now, because now I've got 2 test methods running and they both passed. Okay, so far this is just testing basics, nothing really interesting for data scientists. So now, let's look at things that are unique to data science work for writing tests. So the first thing is that we probably work with randomness more than most programmers and developers do. And so we have to kind of think about how you can test for things that are random. So one thing that we can do is, if we have a way to measure our output without being exact, that's going to be the best. So I'm going to have a method here that generates a random normal distribution with a mean of 100 and a standard deviation of 25, and it's going to give me a list of 1,000 numbers that are from that normal distribution. So if I want to test that that output is valid, I wanted a way to say, if you look at these 1,000 numbers, are they probably from a normal distribution, right? And that's not something that you can just look at and tell yes or no. You could make a plot of the distribution, kind of eyeball it and guess. But there are methods that'll do that and give you a measure of how close it appears to be to a normal distribution. So let me go back into my test file. For this one, I'm going to need to import something new, which is from SciPy stats. I'm going to want to import the normal test function. Okay, so now let's write a test for generate random normal dist. And so for this one, what I'm looking at is, when I run this function, am I going to get a result that is close to what I expect it to be? So the first thing I'm going to do is I'm going to call the function. Okay. The results are, it gives you 2 variables as the output, and I actually don't remember what the first one is, but the second one is a p-value, which basically just tells you how likely it is that this is from a normal distribution. And that's the one I want. So we're going to say okay, so now I have generated numbers from a random normal distribution. I have put those into the normal test and figured out whether it thinks that this is normal or not. And now I'm going to examine the p-value and see if it's what I want. So p-values are values between 0 and 1. They're probabilities. In this instance, the larger the p-value, the more likely it is that it came from a normal distribution. So that's what I want. So a good p-value would be really small. Maybe I could say something like greater than 0.01. So that would mean there's like at least a 99% chance that this is truly normal. So let's start with that and see if we can pass or fail that one. Okay, so that one passed, but I'm not going to get the same result every time. And if I ran this 100 times, I would expect that at least once I'm going to fail that test. Right? But if I'm saving these benchmarks as I go, if I'm logging my testing output, if I did fail that one time, I could go back and look at the results that I had previously and see if that was reasonable or not. All right, and so the last one I think I'm going to probably have time for is I have a method in here called the classify posts pipeline, and so this is really just a basic sklearn example. It uses sklearn to load some newsgroup data and then pass all of that through a text processing pipeline. So it does, it's got a vectorizer, TF-IDF transformer, SGD classifier, and then it runs a grid search over that to try to find the best parameters for each of those. So this one is going to have varying results because if you look at the SGD classifier, that's stochastic gradient descent, and stochastic basically means it's going to change. So every time I run this, I'm going to get slightly different output from this. It's going to build a model for me, but the model is going to vary from run to run. So maybe the first time, I'm just going to run it and see what my results are so I can have a baseline, and then I'm going to write a test around that. So I'm going to have to do a few more imports here. Let's see. Probably want to say, oh, maybe not. Maybe I have everything I need. So we're going to say test classify posts pipeline. So for this one, first thing I want to do is run the original method. Save the results, and now I'm going to examine this grid search object. And I'm going to look at the best score that I get, and I want it to be at least 0.95. Right, and so same as before, I don't actually know if I'm going to get that score on my first run. I probably won't. If I ran it 100 times, I probably would get a score that was over 95 a handful of those times. Right, but my goal here is not to have perfect results every time. It's just to set a baseline and then be able to measure against that baseline as I go. So I'll run the test and see if I pass or fail. This one's going to take a few seconds to crank through because it's doing a grid search, so we'll just sit here patiently while I sip some water. All right, so this time I failed my test. I wanted it to get a score of at least 95, and I probably didn't. If I scroll back up through the output, usually it's nice enough to show you where you failed. So it captures the standard out and prints it to the screen when you fail a test. If you pass your test, you don't need to see your output, so it just suppresses it. But by default, it'll print out the standard out when you fail a test. So here's what I printed out. My best score this time was only 0.939. I needed it to be at least 95 to pass the test. So I could go back and just lower the threshold, or I could use a Pytest feature called xfail. So xfail, you can just use it as a decorator and say Pytest mark xfail. And what xfail is an expected test failure. So I know that I don't have this model working to my liking yet. I want this test to be here because I know what the output is supposed to be, but I'm not passing the test yet, and I'm going to tell Pytest that it's not passing by marking it as an xfail, and then an optional parameter here is I can give it a reason, just maybe so I don't forget. So the reason is, baseline score was 0.939. Right? So when I run the tests again, it'll still fail, but now it'll be marked as an xfail and it won't count against me, and it'll let me know, oh, that's something I need to keep working on. So we'll just sit here and wait while it plugs through again. Cool, so now instead of saying 4 fail, or 3 passed and 1 failed, it says 3 passed, 1 X failed. And it'll still give me an X right here in my output. But now I know that that's supposed to happen, and it's not going to count against me. If I run a coverage report, or if I view the output I'll run an HTML report in a minute. It'll mark those separately, so I know the difference. There's a few more examples that I have in the repo. So if this is interesting to you and you want to look at a few more things, some other features that Pytest has that are handy for doing data science tests. One is fixtures, and fixtures are basically anytime you want to set something up and have it used multiple times for lots of tests. So if you have a big data set you need to load, or if you need to make a connection to something and you just want to run it once instead of having to run it every single test method, you can just use the Pytest fixture decorator, and then whatever it returns will be something you can use in all of your tests. The way that you use it is you just take that and put it as an argument to your test method. All right, so my Pytest fixture was called sales_records. I pass sales_records to this test average method, and it'll be able to use that variable. So we looked at xfail in the code. I didn't have one that was called skip. Skip does exactly what you think. It just doesn't run that test. Xfail runs the test and then tells you it failed, but you knew it. Skip just passes over that test until you remove the mark. Another thing that might be useful that I didn't have time for in the talk is that you can compare images and plots. This is a feature available in Matplotlib. So if you are the kind of data scientist that produces a lot of plots, a lot of reports, and you want to make sure that your plots are consistent, or if you want to make sure that it works on the same across platforms, or if you have somewhere that you're going to be deploying your code to and you want to make sure it runs the same on that server as it does on your local laptop, you can generate test images and then have your test check and see if the images made on the development or on the deployment environment match those that you had on your test environment. And then, like I said, benchmarking a model like I was showing at the end there. So that one is really not something that you would expect the normal software engineers that would need to do that would be really valuable to us as data scientists. So another thing about Pytest that makes it really nice is there are lots of configuration options for it, and their documentation is really great. I recommend that if you start writing these tests, you spend some time to look through it. There's tons of features available, so I have a few that I included in my repo. I put all of these in a shell script called test.sh just because these things are easy to forget. And this way you can run the same way every time. So these are the options that I have. The first one is it saves an HTML test report. I'll pull that up in a second. We'll look at it. The self-contained HTML flag just says put it all in one file. Don't have like a CSS file and whatever other separate files. The other thing you can do is you can do coverage reports, and so this is something that maybe you are not familiar with yet, but if you talk to a developer, they are definitely going to know what this means. This means that it tells whoever's viewing your output how much of the code you tested. So if you have 100 lines of code and you test 3 of them, your test coverage is 3%, right? So maybe it's not super valuable to you, but it will be valuable to whoever else is going to be looking at your work. And then cov report term missing, this is just a coverage report setting, and just tells it make a report to the terminal and include the missing line numbers so I know which lines weren't tested yet. And then the -r app flag tells it what test results to show you. This basically just shows you all of the test results. And then the very last argument is where you're going to be testing. So on mine, there's a folder called test, so I need to put that at the end of the command. So if I go back over here, I have all of that saved in a shell script. I have all of that saved in a shell script, and it also checks and makes sure that the logs directory exists before it does it. Right? And so this way, all I have to do is go to the root directory of my project and say run test.sh, and it'll do the same thing every time. So I can do that now. So it doesn't really look any different. It still just runs the tests. But the one thing that this does that the other one didn't is now, because I have the HTML flag, it'll create an HTML output file. And so when it finishes doing the grid search one last time, I'll go ahead and pull up that HTML file and we'll see what it looks like. Okay, so I've got my test logs. We'll open up that HTML report. And so this is just the default configuration for Pytest's HTML reports. You can configure all of this output, and you can add in extra information. You can add in special tags for only things that fail, only things that X fail. You can add in, if you want to like present what the current variable is, you can add that in here too. But basically, if you fail or X fail, it gives you a report showing you all of the things about why you failed. And if you passed, it doesn't really tell you much of anything. It just says, I passed, and here's the test method that passed. Cool, and so this is just one of the things that I like. It's a nice, pretty way to view results. And if you save these HTML files as you go, you can use this to look back and compare your results over time. All right. So that's the end of my presentation. Just my conclusion, Pytest is really easy to use. You can get started right away. So go ahead and start now for whatever it is that you're working on. Write some tests and see how you like it. It'll earn you the trust and respect of your peers, and you can use it even if your code is stochastic. So if you get different results every time, you can still write tests for that. So, questions? What would you like me to talk about?
Well, it's the mocking question, and whether or not you should build like a sample data frame that looks like the real thing but doesn't have 50 million rows, or whether you should build a complete mock for the data frame and make sure that it's being exercised with the right methods and arguments.
Okay, so mocking, when referred to in testing, basically means you don't want to have to do something for real. So you don't want to connect to a real database, or you don't want to load a real data file. You want to do something fake that's not going to take as long, or it's not going to make external connections. And so the question is, when you have a huge data frame and you want to do tests on it, should you test on the real huge data frame with millions and millions of rows, or should you make a mock of it? And that's really, I can't answer that question because that's going to depend on the circumstances that you're in. If you are in a mission critical environment and it's important to make sure that every single thing is valid, then you should use your whole data frame, right? If you need to make sure that there is not a single nan in that whole thing, then go ahead and use that. But for me, I don't want tests to run a long time. If I have a test that takes half an hour to run, I'm not going to run it very often, right? So I would say mock it down to a reasonable size so that you can run all of your tests in what you think is a reasonable time.
Yeah, sir.
Thank you.
Thank you for your talk. Very interesting. How do we convince people to write tests? I find it very challenging to convince anyone to invest in them, including senior people. They're like, just quickly do it. We'll get to testing later. It never happens. Are there any statistics, for example, showing that good tests help you over the long run?
Oh yeah. This is something that is not unique to data science. This is something that has been consistent throughout the history of data science. People don't like writing tests because it's not easy. It takes time away from doing what you consider to be your real work. It doesn't get you like fame and fortune. And depending on what kind of manager you have, some people don't see it as being valid output, right? Like if they're measuring how much code you're producing, they might not consider your tests to be part of that. But there is a plethora of research going back decades that says that testing is great, and the more tests you write, the better. There's basically no limit to how much it will improve your work. It's going to increase your efficiency. It's going to save your company money over time. All of that data is definitely out there.
Hey. So I guess if
we wanted to, this is really loud, to learn more about how, as a research engineer, to do better testing, do this kind of more integrated kind of testing. Are there any kind of like books or people we should follow? Like,
I don't know about books or people you should follow, but one thing that I think would be a really great resource if you're like just getting started is included in my README. At the bottom of my README, there's a couple of resources, and this data science testing tutorial is a really excellent repo that shows some of the things that I showed, but a lot more as well. And so I would say start there. There's a book about test-driven development for data science that I know is really valuable. So.
Hi. I just wanted to make a comment about the convincing people to write tests, because this is something that seems to come up a lot. I've, I guess, been very fortunate to work in multiple places with TDD as like something they practice. And I can't tell you the amount of times I've said, oh man, I'm so glad that test was there, when I was working on another piece of code that somehow affected the logic of another piece of code. And the time like you save in debugging is, like, it should speak for itself. And I think what is hard for most people is to get started. So if you want to be that person, you have to set it up for them. And for every like pull review, pull request, or whatever, you could be like, hey, where are the tests? And don't accept it or something. Like, it just, it's the seed you plant and it grows, and it's so helpful.
Yeah, thank you so much for your anecdote. So one of the great things about tests is once you've written a test, it doesn't change. So you can change your code, but the test won't. And if your code no longer does what it's supposed to, you'll find out.
Okay, we're out of time, so let's thank David again.
Thank you.